Good evening everyone. Smile.
All right, we are live. Hello, everybody, and welcome to the stream. I hope everybody is doing well tonight. RCW, thank you so much for the Tier 1 sub. I really appreciate that support. Thank you very much for that. Penguin Operator, good to see you as well. Eyeless42, hello. Once again, we rise. Indeed. Indeed, we do. So tonight we're going to pick up where we left off last night. I did add in a couple of lines of code here, but I didn't really get a chance to get much stuff done offline, which is fine. We'll continue where we left off. Before we do that, though, I do want to just take a quick second to thank the supporters of the channel, starting with our highest tier of subscription, our elite partner, Javier Lazaron, followed by our partners, Gobolis Inc. and Matt Osgard. That's the second tier there of support over on YouTube memberships and Patreon, followed by the list of supporters you see here scrolling on the screen now. They are a combination of the other tiers of support over on YouTube memberships, Patreon, as well as Twitch subscriptions. So thank you all very much for your support. It is greatly appreciated, and it helps me cover the costs associated with running the channel, things like software licenses, hosting fees, things of that nature. RCW, you are actually in there, so it did update in time. But yeah, thank you so much for that. I really appreciate the support. And I would also like to thank all of you guys, the viewers, whether you're joining us here live on the YouTube side or the Twitch side, or if you're catching the VOD after the fact. Thank you very much for being here, because without you guys, this project and this channel would not exist. So I appreciate each and every one of you. Apotham, good to see you as well. All right. So with all of that said, basically where we had left off last night was we just had this sort of tight loop here of submeshes in our serialization routine. So, we hadn't really filled any of that out yet. We just kind of started putting together this after we finished the deserialization last night. So just as a reminder, the way that this works is we take a constant pointer to the asset that we want to serialize, and then we serialize that to a block of memory, which gets returned, and then we also report the size of that block of memory once we're all said and done. So last night we had filled out the header, at least most of it. We will obviously be coming back to fill in a property or two, specifically this here, once we get to the very end. But for now, we're basically just going through and creating all of the arrays and structures that we need to actually be able to write this thing out. And then from there, we'll go ahead and create our huge block of memory and copy everything over to it accordingly, and so on and so forth. Okay. So, with that being said, from last night, the biggest difference here is that I just added a little bit of logic here to iterate over all of these submeshes to get the entire size of the submesh index and vertex buffers, so that we can go ahead and allocate those. So all we do is we just loop through all of our submeshes, take a look at what type of geometry that they have, and just tack on the size accordingly for the vertex buffer, and then the index buffer is obviously always going to be U32s, and then we allocate those things in preparation to fill them with data later. So the other thing that we need to do is, let me see, the submesh type is actually, these are actually wrong now that I'm looking at it. So what I had done was we had sort of a to-do here last night. Let me make sure I'm not coding behind my head here. We had sort of a to-do here last night to define another type. And we had this K-asset model mesh type here, which is, last night we were thinking, oh, just mesh type is what I had in here. So here we're actually creating an explicit type for this. And as far as the assets go, it knows about static or skinned geometry. However, the names on these are wrong. So we should do, I guess we should probably do K-asset model mesh type. And then we should do, again, K-asset model mesh type, right? And then over here, this should be K-asset model mesh type static and skinned. And then there was one other place down here where we had that here and here. And the reason for that is because we are looking at the assets model submesh data type, right? So that is specifically that type. Now, we do also have, at the top here, we do have the K3D mesh type. However, there's a strong chance that some of this logic actually gets split out away from the game engine. I got thinking, there should probably be one sort of for the file formats and then a separate one for what the game engine supports, because maybe the file format will wind up supporting some other things that maybe the core engine won't support. There may wind up being a mismatch there somewhere of other data types that we have. So I went ahead and created unique types for those. For now, they match up, so not a huge deal there. All right, so for that, we then, once we have the entire size of the buffers, we go ahead and allocate them, and then we iterate, once again, all of these submeshes. And again, we have to grab the vertex size of each one, which, could we cache this? Yes, we could. We could store it on the submesh, I guess. Actually, yeah, I'm not going to store vertex size on there. Yeah, it just doesn't make any sense. It's quick enough to look it up here. So we go ahead and grab the vertex size again. And then this time we calculate a V size and an I size, which is basically the vertex size of an individual vertex, whether it's vertex 3D or a skinned vertex 3D, and we multiply that by how many vertices are in that submesh, and that gives us the V size, and then the I size is just how many indices we have, that multiplied by the size of a U32. From there, we go ahead and we copy memory into the vertex and index buffers using these vert and index offsets. So those start off at 0, and every time we come across a submesh and we upload or copy data into it rather, we go ahead and we increment those offsets by that amount. And that is how we keep everything loaded in that buffer as we sort of continue through the loop. Last couple things that we have in here in terms of meshes themselves, of course, we keep the vertex and index counts for each one of those things. So we just pull that from the submesh data. And then the center and the extents, we pull that from the submesh data. And then here is sort of the opposite of what we were doing above when we deserialize, where here we are actually adding an entry to our binary string table. And so just as a refresher on the way that this binary string table works, so we have this binary string table add, obviously that takes a pointer to the table, and a constant character array for the string. And so what that returns is a index of the added string. So it internalizes that string and packs it into that sort of huge binary blob that it has internally, and then returns to us an index or an ID. And that ID is what we use here for name IDs, in this case sub I. So we use the same logic once again for material name IDs, and then we just use material name. And you'll also note here that since submesh name and material name are both K names, that means that we have to get the original string. So we just do a K name string get, which gets the string from that hash, and it just returns that directly. It does not return a copy. It returns a constant pointer to the string if found, right? So that is that. We probably should, though, thinking about this, we should probably don't want to use 0 here. We don't want to internalize this if there is no name. So there's actually one more step we need to do. So let's do constant character array name equals, and then we're going to take this and put that there. And then we'll do if name. And then we'll go ahead and do name here, and then do that, right? So we only really want to internalize this if we actually have the name. If we do not, then we can do, let me think about this. We should probably, you know what, we can make this a ternary, make this a little bit, right? So let's do name. If we have name, we're going to call binary string table add and use its return value. Otherwise, we're going to use invalid ID U16. Okay, so that makes sense there. We'll also do const character array material name, and that's going to be equal to, and we'll go ahead and grab this. Right, and then once again, here we'll go ahead and say if we have material name, then we'll use that. We'll pass material name here. Otherwise, we'll use invalid ID U16. Right, so invalid ID U16 basically just says we don't have a name for this thing. Okay, so that's a little bit safer. I think that's how we should handle all names. We only really need to internalize them if we actually have something that's returned there, right, from here. And kname string get, I believe, is smart enough, if I remember correctly. Let's see, do we do... We technically would do a binary search tree find on that. I think because of this, if we pass 0 here, it won't return anything. However, I'm going to shortcut that so we don't even have to go into this at all. And I'm going to say if name equals invalid kname, return 0. Right, let's just shortcut that. And then, of course, if we don't actually find the string from the hash at all, we'll also return 0. So, minor update there. let's say also returns 0 null if invalid kname/0 is provided as the name. Right, let's make that a little bit more robust. So I suppose that, you know, we don't necessarily have to step through as much code to make that same determination. Okay, and I believe that is everything that we need. So we have centers, extents. Did we do mesh types? I don't think we actually did mesh types. That might be the one thing that we're missing. I don't think we did mesh types. So in our spec, we had said mesh type. 0 is vertex 3D, 1 is skinned vertex 3D. Now, those just happen to line up with this perfectly. However, it's possible that maybe they won't someday. So I think what I'm going to do is I'm going to also come in here and say, we'll say U8 mesh type, and we're going to just say 0, right? And then we'll do here mesh type equals 0, and we'll do here mesh type equals 1. And the reason that we're doing that explicitly like that is, like I said, you know, the order of these might change. We might add new ones. And so we don't necessarily want to just, you know, rely on that directly. So I can do submeshes, mesh types, sub I equals, and then we'll do mesh type. And that will be identified there as well. And that is how we are going to essentially translate from our model submesh data to our submeshes struct that we have here for our K3D format. And then we'll be able to take all of this data later on and write it into the file. Let me see. Thank you for the follow. I appreciate that. Welcome. Okay, so the next thing that we're going to need to do is bones. So bones, I think, are actually very, very straightforward. So let's go ahead and do K3D bones. We're going to call this bones, right? And actually, let's do name IDs, right? So that's going to be equal to KLXC array, and that'll be an array of U16s, and the count is going to be header bone count, right? And then we have offset matrices, which is going to be KLX type C array again. This time the type is going to be mat4. And the count is going to be header bone count once again, right? And so that's all we actually need to do for all of the bones in here, is we just have to essentially fill those things out. So the simplest way is going to be to just loop through them, right? Iterate them. So we'll say U16I equals 0. I is less than header bone counts plus I. And then we can do, let's see, we can do asset bones sub I And we'll do, oh, we have name, offset, and ID. I guess we don't need, I don't think we need the ID. Actually, we might be able to get rid of that. All right, so let's do name first. So name IDs is going to work kind of similar to what we had up here. So we're going to do constant character array, and we're going to just say name equals kname string get, and we're going to pass the name, right? And then we'll say if name, or I guess actually we could just do the same thing as we did above again. We can do bones, name IDs sub I equals, and then we'll just say, do we have a name? If we do, then we're going to do binary string table add, the address of string table, and then the string we want to add is going to be name. Otherwise, we'll just do invalid ID u16. Right, so there's our names. And then the only other thing is matrices, right, which is actually pretty straightforward. So we'll just do bones, offset matrices sub I equals asset bones sub I offset, right? And that's it for bones. That's all there is to it. Nothing really crazy to write home to about that. All right, so I'm actually just going to copy pasta this because a lot of the logic is going to be the same between nodes and bones. We just have to change a lot of the things that say nodes to bones. So we're going to do node counts and node counts. And let's see, the next thing that we need in our nodes is going to be local transforms, which is also going to be a map for, so that's perfect. And then we're also going to need one more thing, which is going to be parent indices. And I think that's U16s, if I remember correctly. So we'll do kalloc type C array, U16 is the type, and then count is going to be, again, header node count, right? And I think that was the correct type. Yes. Okay. So here's our nodes. And then once again, we'll loop through all of our nodes here. So this is going to be asset, nodes, name. And so this will be nodes. No, oh my God, I typed it wrong twice. There we go. So this is going to be name, binary string, table add, name here, or invalid ID, U16. That looks fine. And then local transforms is what this is going to need to be. This is going to be nodes. I keep typing that wrong. Local transform. And then nodes, parent indices, sub I is going to be asset nodes sub I, parent index, right? And that is nodes. Let me just make sure I don't have bones typed in there anywhere. Nope. Okay. All right, so that is bones and nodes. So those are ready. Animations are going to be a little bit trickier, just because we have a couple of layers of information there. So kind of like when we deserialize these, when we go to serialize them, we'll do animations first, and then animation channels after that. Let me just catch up on some chat, though. Watched your streams almost 2 years ago and stopped because of my government blocked almost all the internet. Oof. So much progress. You already rendered Sponza demo scene. Yes. Want to know your opinion. How do you think rendered glyphs for AI inputs is better than traditional tokens represented as text? I'm not sure what you mean by rendered glyphs for AI inputs. unless I'm misunderstanding what you're asking. Yeah, would you mind clarifying what you mean by that? Naturally curious. I am doing well. Thank you for asking. How are you? PRC for multi-platform compiler shenanigans, or are you just like hardcore memory handling? Yeah, I mean, we do have multiple platforms. We have all of our platform code. In here, right, for the specific OSs that we support now. So I've got one for Linux, one for Mac OS, and one for Win32. This Nix is basically some shared platform code between Linux and Mac OS. But yeah. Rendered in 3D context. An AI framework for scaling the context length through visual text compression. Something I haven't looked into, to be completely honest. Yeah, I can't speak on it because I don't know enough about it. I think I roughly know what you're talking about, but like beyond that, I'm not really sure. We do text the traditional way here with glyphs. So, if anything, we're probably going to be stepping it up to sign distance field rendering at some point, but for now, not really. Would seem to imply a vision-based model that gets broken down into tokens in the end after depatching. Yeah. I have. I don't know enough about that, to be honest. I don't need anything really fancy when it comes to text rendering, so we've got two ways of doing it, and I think that's going to cover all of our needs. We have support for bitmap fonts, and then we have support for what I call system fonts, which are just reading in true type fonts and generating glyphs off of that. And then the rendering of those two is almost identical between the two of them. We just render those two. For the system fonts, we render that to an atlas, and then we use that to render it the same way that we do bitmap text, and it's fast. So, yeah, we're not going to be, like I said, as fancy as I'm going to get is probably upping that to a signed distance field type of rendering, just for some additional ease of effects like outlines on text and stuff like that. But other than that, I don't think we're going to get too fancy. Okay, so animations. Animations are relatively flat, except for channels, right? And that's why we have animations, and then animation channels kind of comes after that in a separate sort of section. So we're going to say K3D animations. We're just going to call this animations, and we're going to set this up. The name IDs is going to be KLXC array, as you might have guessed. That's going to be a U16 array, and the length is going to be header animation count. And then we have, we can actually just kind of duplicate this a couple times. And so we have total channel counts. We'll need to get that in a second, but let's do ticks per seconds, right? So that is going to wind up being, let's see, that is going to wind up being an array of F32s. And then we have the durations, which is also going to be F32 array. And then what's the last thing we have here? Channel counts, right? So that's channel counts per individual animation, right? So we've got all that, and the last thing that we'll need is we're going to need the total channel count. So right now I'm gonna initialize that to 0, and we're essentially going to loop through all animations and take a total channel count as we continue through those. and go from there, right? So to get all of this information, just like the other sections, we're going to do a for u16, I equals 0, I is less than header animation counts, and plus I. And in here, the very first thing we're going to do is we're going to say animations total channel count plus equals. And then we'll do assets, animations sub I, channel count, right? So we'll go ahead and keep a running tally of all of those channels. And then from there we can do animations, and we can do the, I guess we could do the channel counts sub I is equal to asset animations sub I channel count. And then animations durations sub I is equal to asset animations sub I duration. Animations, let's see, ticks per seconds sub I is equal to asset animations sub I ticks per second. And then name ID, I think, is going to be the last thing that we're going to have to put in here. Yes. So we need to do a constant character array, again, called name. And that's going to be equal to kname string get. And we'll do assets animations sub I name. And then we'll say animations name IDs sub I equals, if we have a name, then we'll do a binary string table add, passing the address of the string table, and then the name, of course. If we don't have that, invalid ID u16, right? And that is pretty much going to do it for our animations, right? Now, our animation channels is going to require us to essentially loop through this structure one more time. It's not the end of the world, but you know, it is what it is. So we'll go ahead and handle that accordingly. Before we do that, though, we do need to set animations. Oh, wait a minute. Didn't we already say? No, we're already taking the total count here. Okay. So here we'll do, let me actually space this down one. And we'll say K3D animation channels. And in here, we've got a whole bunch of different things, right? So we have name IDs. And so this is going to be Kalec type C array, U16 again. This time, though, it's going to be animations total channel count for that. And we're going to duplicate this a few times. And instead of name IDs, we're going to have, let's see, we're going to have all of the counts is what we're going to set up first. So we're going to do, I guess we'll do position counts. And I don't recall, was that a U32? Yeah, it was a U32. And then we'll have rotation counts. That's also U32. And then we'll have scale counts. That's also U32. And then we're also going to need offsets into all of these things, right? So position offsets, rotation offsets, and then one more, which will be scale offsets. And I believe these are also U32. Probably should have copied a different line there, but there we have it. Okay. So the only other thing that we have to figure out is the data buffer. right? How large do we need this data buffer to be? So to get that, we're actually going to have to count up, actually, no, we have the total channel counts. We can actually figure this out on our own. So, no, we are going to have to iterate each one. So essentially what we're going to have to do is take a total count of all the position counts, rotation counts, scale counts. Keep a running total of all of these things. Multiply them by the size of the type of data they hold. So just for reference, here's a channel up here. So positions are a key vector 3, scales are a key vector 3, and rotations are a key quat. And I think we need to actually do this. We need to make sure we do this in the same order that we are extracting it in deserialization. So it looks like we do position, rotation, then scale. So we just need to make sure that we write to that in the same order. Let's do notes, write position, rotation, then scale per channel. I think that's what it was, right? It was per channel. Is that the way we did that? Yes. Okay. Okay. So like I said, this is probably going to be the most complicated part of all this, and it's not really all that complicated. It's just, it's going to be a lot of sort of reasoning about logic. Let's see. From Lake, good to see you. How have you been? Is this the second or third custom file format in this series? Oh, this is like probably the 8th, I would have to say, if I sat down and actually totaled it up. Because we actually have a custom texture format. We have the KSIN files, which we use that file format for a lot of stuff. So you could technically count each one of those as like a file format. We used to have a couple of iterations of material file formats, but those were converted to KSIN. We have our scene file format. We have, we've got several things, I would say. A lot of those have been compressed into, not compressed, that's not the word I'm looking for. Combined into using just the standard KSIN format. But the binary versions of those, when we eventually get ready to package and ship, we're going to want binary versions of a lot of that stuff. And so we'll have to do this for some of those other proprietary formats as well. You started your own USB microchip programming. That's pretty cool. That sounds kind of like a neat project. But yeah, nice. Awesome. Singy, good to see you as well. How's it going? Let's see. Referencing a paper that kind of takes screenshots of LLM history, it actually has nothing to do with drawing glyphs for what it's worth. Oh, okay. Yeah, see, I was a little bit confused on that. So that's fair enough. Doing rendering about a year ago, got to buy a paper called Real-Time Texture Mapped Vector Glyphs from SIGGRAPH about 2005, 2007. Thinking about... Okay. You're thinking about yours within the context of a renderer for an application in machine learning AI. Interesting. See, to me, that's too fancy when it comes to text rendering. I don't need all that fanciness, so I probably wouldn't go that route. I definitely would not need all that stuff for what I'm doing anyway. All right. So for channels, we are essentially going to have to go through animations again. So let's grab this, because that's going to be the first thing. And then within that, some of you might be excited for this. We are going to use, let's see, this is going to be animations, channel counts, index C. We are actually going to use C++ again on the stream tonight. There it is, using C++. All right, so for each of these channels here, we should probably have like a trying to think of what all we need to write. So the first thing that we need to do, I guess we should probably have some sort of like global channel ID. So I can probably work this into the for loops, but I'm going to put it here for now. We'll say channel ID equals 0, right? And then for every iteration of this, we're going to do channel ID ++, right? Like I said, I'm probably going to wind up reworking that, but I'm just trying to think this out for now. So the way that this is going to work is we are going to write the channels in the order that they are in the animations themselves, but also in the order that the animations are in the asset, right? So we're going to write the first animations set of channels in that order, and then the second animation set of channels in that order. And that's the way that we're going to proceed. So the channel ID is sort of the overall index into that, right? So we can do channels, and let's see. The first thing we're probably going to want to fill out is animation IDs, right? And so the index for this is going to be channel ID. And then the animation ID's sub-channel ID is going to be I, right, for the animation that we are currently on. Channels, let's see. We probably need let me think about this. So yeah, we should probably write the counts first, then write the data into the data buffer, and then as we write the data into the data buffer, we update the offsets. So let's do the counts first. So we'll do position counts sub channel ID. And that's going to be assets animations sub I, channels sub C, position count, right? And just to make this a little less confusing, I think what I'm going to do is actually create myself a couple of convenience pointers, right? So k-asset model animation, right? And I'm going to say anim equals the address of assets animations sub I. And then in here, I'm going to do k-assets model animation channel, or is it just channel? Model channel, I guess it was. Pointer, we're going to call this channel, and that's going to be the address of anim channels sub C. Right? And so now, all I have to do in here is actually just say channel pause count, right? That's a little easier to deal with, I think. We'll obviously want to do channels, rock counts, channel ID. equals channel rotation counts, channels scale counts sub channel ID equals channel scale count, right? So that's those. And then, like I said, we need to write these in a particular order. So we want to write position first, then rotation, then scale. And I actually just realized we have not set up our data buffer yet. So this is going to be, do I want to do this? I think I'm going to do a k-allocate for this. In the size, we're just going to do channel buffer size. And the memory tag is just going to be binary data. All right. We need to calculate channel buffer size first. So we actually are going to have to do this twice, which kind of sucks. But that's the way it goes when you have to deal with predetermined blocks of memory. It's far better to do this than to keep reallocating in a tight loop like that, right? So all we'll do here is I'll do a U32 channel buffer size equals 0, and then we'll do a channel buffer size plus equals size of, and then we're going to want a k-asset model key vec3 times channel position count, right? And we're going to do the same thing for scale count, and then the same thing again, but using quaternions for rotation count, right? So this will tell us how large our buffer needs to be, and then that way we can go ahead and k-allocate that here and be able to write into it. I suppose the other thing that we should do, we'll copy pasta these here just for reference. So what we'll do is we'll say let's do U32, and we're going to say pause size, and that's just going to be equal, right? So U32 rotation size equals, and then this is just going to be scale size, right? So we have those so that we know how far or how much data to write, and then how far to move the offset into that buffer for each time, right? So here we are also going to have a U32. I guess we'll say a channel data buffer offset, and that's going to start off at 0. And so what we're going to do is, well, actually, yeah, okay. What we're going to do is we're going to do a k-copy memory. The destination is going to be the channels. Well, actually, it's going to be, we're going to have to first cast to a U8, right? And we'll say channels data buffer, right? And then it's going to be that plus the current channel data buffer offset, right? Is going to be where we're going to write that to. And then the source is going to be channel positions, and the size is going to be pause size, right? And then we can go ahead here and say channel data buffer offset plus equals pause size, right? So here is where we actually write in all of that data. All right, so I'm actually just going to paste this in here 2 more times. And we're going to do rotations next. So rot size. And then once again, rot size there. And then the last one is going to be scales and scale size and scale size. Right? And that is almost going to do it. There's 1 more piece of data that we need filled out. 3 more pieces of data, actually. So we have the position counts. Right, that was easy. But we also have offsets. Right, so position offsets, rotation offsets, scale offsets. And then, let's see, we didn't do names either. So we actually need to handle the names as well. So the offset of this, of each one of these things, is going to be where we are going to write to before we actually write to this buffer, right? So what we actually want to put in here is channels, position offsets, sub channel ID. And this is going to be channel data buffer offset, right? And then we come down here. After this is incremented. And once again, I'm going to split this up just to make it a little bit more readable. Rotation offsets is going to be that. And then we can go ahead and split this up 1 more time and do scale offsets, right? So as we're sort of progressing through that buffer, we're keeping track of where the offsets of these things are so that we can easily read them back out of memory. And we're also keeping a moving buffer at the same time, or a moving offset into that buffer at the same time. So we're kind of killing a couple birds with 1 stone here. The last thing that we need to do is the name, and I guess we can actually do that up top. So channels, and then we'll do name IDs, sub channel ID. And that is going to be equal to, we don't have the actual name yet, so we need to do constant character array name equals kname string, kname string get. And that needs to be channel name. And then if we have the name, we go ahead and we say binary string table add, take the address of string table, string table, and pass name. And then if we don't have that, then we'll say invalid ID U16. That should be address of string table. Okay. Cool. So that is that. And I think, let me just double check here. I believe that's all of the fields for, see, we did animation IDs, we did names, we did position counts offsets, rotation counts offsets, scale counts offsets, and the data buffer. And then we filled out the data buffer. So there we are. Okay. Do we actually have a total? Did we actually keep the total channel count in here? We actually did this before, I think, didn't we? Yes, we did. We did grab that too. Okay. I think we have everything we need. So now we can actually start thinking about how to write actually all of this to a binary format that we can actually read in later. Let's see. Hi, can you talk about your choice of using C versus a reduced subset of C++? Deciding between both for a little game I'll be making. That's fair enough. So I went back and forth on that for quite a while before I started this project. And, my C++ has always looked remarkably like C. I don't really use most of the features in modern C++. I don't have a reason to use them. The only things that I was truly using was the null pointer keyword, operator overloads for math functions, occasionally function overloads for things like logging, or maybe like a type safe min max, that kind of thing. I swear there was something else. That might have been it though. Constant expression for things like compile time string hashing, right? But I decided, I'm like, you know what? I think I can live without those things. Let me, as an experiment, as with everything else of this project, it's an experiment. We try things. Let me try writing and see, and we'll see, right? And so I did. And one of the things that also kind of led me in that direction a lot is, the C compiler is a lot quicker. So building is much, much faster than C++, because it's much simpler language. And I wasn't using most of what was C++ offered anyways. So, I've learned to sort of do without those things, and I think I'm better off. I think the code base is better off without that. I don't really use a lot of the standard library things. I wasn't using any of the template library or any of that kind of stuff from C++, so it made no sense to actually use that stuff, I guess. So I chose C, and this code base is plus or minus some of the things we've done refactoring. It's probably around 71 to 75,000 lines of code at this point, ish. No regrets. So take that for what you will. Let's see. I'm going to have to skip some of these messages because I can't read all of those. Tiny C compiler for the win. Yeah, I should. I've had thoughts about writing my own, but I don't have time for that. Not anymore. Guessing no use of templates at all, even simple ones. Nope. Don't need them. Wound up not needing them. Yeah, so I hope that makes sense. Cool. Do we plan to implement occlusion culling? I don't know. The whole theme with this engine is I'm kind of just writing what I need to write, and I'm trying not to write too much else that I don't really need. So if we get into game development, I'm like, you know what, I really could use occlusion culling for, because it's causing performance problems not having it, and I need to action it, then I will do it. But as of right now, I don't think that's going to be an issue. Particularly for the style of game that we're doing, I don't think it's going to be necessary, but we'll see. Cool. All right. So, why is that bleating? Probably because block is not declared. Okay. All right. So, what we need to do now is actually write out to this file, because I think I've gotten all the sections completed here. So the way that this needs to work is we need to write the header first. And the header is pretty much just a flat write of this data structure, right? So the header that we created up here, this is essentially going to be a flat write. The string table offset we do need to calculate before we can write that, though. So essentially what we need to do is we need to figure out what the total size of the file is all the way up until after the strings begin guard. So to do that, we're going to have to get the size of the header, and then take into account the begin guard, which is another 4 bytes. And then we essentially have an array of these data types. So we'll have to figure out what the size of all of those arrays is, and then the size of the vertex and index data buffers at the end. We'll have to figure out what that is. And then after that, we'll have to do, the bones begin guard, name IDs and offset matrices. Again, that's just 2 array sizes. That'll be easy. Same with nodes, just a guard and 3 arrays. And then animations is going to be a guard, a single number, and 4 arrays. And then animation channels will just be a guard, and then a bunch of arrays, and then another data buffer. And then after that point, we'll just have a guard, and then after this guard is where the string table will be. That number is what we can plug into here. And then we can go ahead and write everything out to the file, essentially. So, I wonder if it would make more sense. I think what I might do, instead of waiting to write all this stuff out and trying to figure it out ahead of time, I might just write this header to the block of memory. Well, no, I can't do that because I've actually got to calculate how big of a block of memory we need. Okay. All right, so there's one more thing that we're going to have to do then. And that's going to be all the way down here. For the strings, we are going to have to do binary string table serialized, right? So that's going to take the address of string table. And then the out size is just going to be a U64 string table size. And that's going to be string table size. And then the string table serialized block is just going to be that, right? So we need that. And essentially what that's going to do is that's going to take all of the data structures that are within the binary string table, flatten them into a large block of memory that we can then serialize into this file along with everything else. All right. So I guess what I really should be doing is keeping a running tally of size as we go through all of this. I guess that makes the most sense. So let's keep a U64 total block size. And we're going to keep that at 0. And after we essentially pass each section, we're just going to do a total block size plus equals size of header in this case, because we can just use that directly. Why did we do this one this way and all the other ones not this way? Let's just make that a little bit consistent. Okay. Do we have a utility So I don't have to do all of this all over the place. Do we actually have a utility that will tell me the size and bytes of this? I'd rather not have to do this manually all over the code base. I guess I could, though. It's not really that big of a deal. It's just this, right? It's just kind of error prone is all. Let me look at the spec, because I already feel like I'm missing something. So header, yeah, I'm missing the submeshes begin guard. So total block size plus equals size of U32. Submeshes begin guard. Okay, so I have that, and then I think it's just literally all of these arrays until we get to the vertex data buffer and the index data buffer. Okay, so I guess it's kind of poopy, but I guess we'll just do it here. So it's going to be the size of, I wonder if I should, you know what, I think I'm just going to do this actually. So instead of, I guess I want change forwards. Yeah, total block size plus equals. Just going to do this a few times. Right, and then here I'm just going to do, oops. Quick multiplication here, and then at the end, do that. Okay, and then this needs to be size of all the way down. Did I get that right? I think so. Oh, I'm also missing an opening. There we go. Okay. So we just move forward by that much. This seems like a lot of work to do to avoid realix, but I feel like realix will just be slower than doing it this way. All right. So I guess what we actually need to do here is this just needs to be total submesh vertex buffer size. And then same thing for the index buffer size. To move those forward. And then for all of our, this is actually setting up the submesh data, so we don't have to do anything with that. We'll just need to do the bones. So this is going to be, let's see, I think we already did. We need to account for the bones guard, right? So bones begin guard. Let's actually move that down here. This is going to be nodes begin guard. So here, this is basically just going to be total block size plus equals size of U16 for the name IDs times header bone counts. And I think we were actually wrapping this in parentheses just to be explicit. And then same thing here, but with mat4s. So that'll move that. And then I think we can actually do the same thing again after nodes. Plus one more U16 after that. And instead of bone count here, that's going to be node count. Right? Then we have the animations guard. And then, let's see. That's going to wind up being essentially another one of these guys. Right, so this is going to wind up being, let's see, name IDs, channel counts. So let's replace this one. Let's make this one the F32 for ticks per seconds, and then another one of those for durations. This all needs to be animation counts. And then, of course, we have the last count for the total channel count, which I think is a U16. Yes. Okay, so that looks pretty good. And then the channel buffer size and the size of these arrays are the only other things we have to take into account. So we have the begin guard. So this is going to be the animation channels begin guard. And then let's just grab this, put this down here. So let's see, this is one U16 and the rest are U32s. So let's see, we have 6 U32 arrays, so we just need a couple more of these. There we go. And then the data buffer itself we know is the channel buffer size, so we can do total block size plus equals channel buffer size to take that into account. And then finally, the string table is the last thing. So we need the we need to take into account the guard for that. So this is going to be the strings table begin guard. And then we have that string table size. So we'll do total block size plus equals string table size. And that is going to be the entire size of the block that we need to allocate. So now allocates the data block and copy all data to it. Incidentally, it would be at this point that we would also fill out the header string table offset is going to be total block size at this point, right? Before we add this, right? So that total block size is also going to be where that gets filled out. So tell the header where the string table should begin. Okay. So now we have all the information we need. We can go ahead and allocate the block of memory. So I'm going to do a kallocate rather, total block size. And the memory tag we're going to use is binary data. Oops. Right. And that is going to be just a void pointer called block. Right. And that solves that error. So we have total block size, and I believe this actually needs to output that. It does. So we'll do, the next thing we'll do is just out size equals total block size. Report that. And now we can actually start writing this stuff into that block, right? So we could do kcopy, or kcopy memory. The destination is going to be block. And the source is going to be the address of header. And the size is going to be size of K3D header. Right? So we write the header. And then we need to write the submesh begin guard. So the next thing we need to do is kcopy memory. It's going to be block plus offset. We need to create that. I'll come back to that in a second. The source. How are we going to do this? So I guess we'll do U32 submesh guard equals K3D guard submeshes, right? And so we'll just do a address of submesh guard and then size of submesh guard, right? And then offsets is something that we're going to have to keep up here as well. So we'll say U64 offset equals 0. And then, you know what? I'm actually kind of leaning towards like we should probably have a utility to help us write some of this stuff because this is all very manual. Some sort of binary writer and maybe binary reader. Will your game have a barista with a big beard making coffee for HP buffs? I don't know about that, but you know, I might be willing to put in you know, Easter eggs or references like that. I probably wouldn't reference myself if I did that though, because putting myself in the game is kind of lame, right? But like, I could see referencing somebody I know, like a friend or a viewer or something like that. Maybe there'll be a contest at some point for that kind of thing. Let's see. When I read about Slack/Discord, it makes me more upset because they're banned for my country. Where are you out of, by the way? If you don't mind answering that, you don't have to. Yeah, I'm just wondering where Discord is banned or Slack. Clairvoyance coding, totally easy, confirmed. I don't know about all that, but okay. So we copy the header, which means that we need to offset plus equals size of K3D header, right? Submesh guard is going to be the same thing. Like this right here, this bit that I'm going to be doing this a bunch of times, which is kind of annoying. I kind of feel like we might want to have some sort of utility that does this for us. Or it can just be like binary writer or whatever I want to call it. Write U32 or write struct, where you pass in a pointer to a struct and how big it is. That kind of thing. Write array. And then it would automatically return like an offset to us that it would. I kind of feel like that might be. I'm going to hold off on that now because I don't want to keep like going off on tangents, but I think that's going to be something we're going to want to do before too much longer, I think. Okay, so submeshes are going to be next. So that's the guard for the submeshes. The next thing that we have to add, I believe, is all of those arrays. Yeah, so that would be all of these. These, rather. So I guess literally what I could do oops. I'm just going to copy this for a second for reference down here. I'm not going to use it as is, but we can do, so submeshes, K copy memory, right? The destination is always going to be block plus offset. The source is going to be the address of submeshes name IDs. I should probably verify that I'm reading these in the correct order at the top too. I think that's how I spec'd it out though. Yeah, okay. So the size here is going to basically be size of U16 times header submesh count. And then the annoying thing is I need this size twice, right? So I guess we could do U64 right size equals that, right? And then I do right size, and then I do offset plus equals right size. That's a little bit simpler. So here I would do another U16. This time it would be material name IDs. Right? Like, see how repetitive this is? Like, this is really, like, I need to at least make a macro out of this. This is kind of stupid. U32. I just want to kind of work out the first use case of it before I do that. So this is going to be vertex counts. And then index counts, right? Yeah, index counts, then mesh types, which is a U8. Mesh types. And then centers, which is going to be a vec3. And then extents 3D for extents. All right. And then the only other thing is the actual data buffers. Right, so that is going to be, and I think we actually, didn't we already have total submesh vertex buffer size? We already have it. So this is going to be vertex data buffer, and then right size. This is going to be there. Okay. So we have that, and then we have the index buffer size. An index data buffer, right? And that is how we are essentially going to write out to the file all the way down. So it's not really complicated to write this stuff out, right? I feel like we could make this a little bit better. Even if it's just like a crappy static private function for now and we standardize it later. The only problem with some of this, let me see. The only problem with some of this is we might not actually have these sections. So we actually need to do only write this if there are submeshes, right? Because there might not be. Yeah, naturally curious, you might be right about that. Yeah, I'm not sure which it is, but essentially, essentially, you're probably right about that. How many lines of code do I have so far? Let's see. So this is the game. So the game library itself has 14,000, and then the engine itself 74,000. Granted, you know, some of those are config files and things like that, but yeah. More than one, yeah. I would say more than one line of code, for sure. Okay, so we could do if header submesh count. Then we do all these things. Right? And incidentally, the submesh guard should be there as well. So yeah, I guess that's fine. I want to take this right size out of here though. I want to hoist this up. So we're going to do U64 right size. And then do away with that. Yeah, I wasn't going to do it now, but I think I'm going to do... Let's do static U64 is return type, and we're going to do right binary for now is what we'll call it. We can always rename it later. And so what this is going to do is we're going to say block. So void pointer block. We're going to do void pointer source. And then we'll do U64 offset. Right, and essentially, we're going to do this. Offset and size. U64 size. So essentially, we're going to have, instead of right size, we're just going to use size. Right, so we'll just say size. And then this is going to be source. And we'll do block plus offset, and then return, or I guess we'll do return offset plus size. Right? I'll have to move this declaration to the top. Sure, I guess I'll put it here for now. That's probably not what it's going to be named. It's probably not going to be where it stays, but at least this way, we can actually do away with the right size thing. And we can actually just say right binary. We can just pass block every time. The source in this case is going to be the address of submeshes. What did I say it was going to be? Name IDs, right? The offset is going to be just offset, and then the size is going to be this. Which, actually, we could even specialize that a little bit further, right? But let's just say offset is equal to that, right? So now all we have to do is that. Which that's good. That's a step in the right direction. But I feel like we can do better. So I want to go down here, and I'm going to make another one. And it's going to be return type U64 as well. And we're going to say right binary array. So we'll have void pointer block, void pointer source, and then we'll do U64 offsets, U64 element size, and then a U32 count. Right, and this one will just literally return right binary. Let's see, block, source, offset could be passed as is, and then this becomes element size times count. That way we don't have to do all that stuff in line. I think that makes a little bit more sense. And then we can also have like some convenience ones as well, where we have like a right U32, you know, where we have a value here. I guess this would be value would be there, just to kind of make it match the rest of it. And then here we would have source would be the address of value. And then size would be just size of U32, etc. Right? And I could probably just macro that out and make it a little bit. In fact, a macro might be the better way to go. But for now, again, I'm just trying to like think out a little bit of a way to make this a little bit easier for now, and then we can standardize it later. So there we go. So those are the major ones we're going to need for now. So now we can do, offsets equals right. What is this? Binary array. Block. The source is going to be address of submeshes material name IDs. The offset is going to be that. The element size is going to be size of U16. And then the count is just going to be header submesh count. And then we get rid of that. Yeah, I think that makes sense. So we can switch this to the array version. And then this just becomes essentially like that. Which I guess that's just replacing a multiplication with a comma, so I guess it doesn't really matter all that much, but if we go to macro these things out, it will matter. With the game engine side of the project, have you done much in terms of maximizing efficiency, maybe things like cache alignment and so on, but not limited to trying to make memory efficient? We've done some of that stuff, yes. We need to do a rather sizable pass on some of that stuff as well. So we wrote our own allocators, and those allocators can align memory when they allocate. And we had to do when we wrote our Vulkan allocator because it actually requires stuff to be aligned. So we do have the stuff in place to do that. But there's a lot of other things that I want to do in terms of organizing the memory when we allocate it based on the memory tag, like what we have here, to make certain types of allocations go within certain subpools within our main allocator. Just haven't done it yet. It's in the feature, but so the answer is we've done some of it and there's still more to do. Okay, so vertex counts. That's just going to be vertex counts. That's going to be a U32. And then index counts. Right, so that's those two. And then mesh types, which is going to be U8. So mesh types, that's just going to be U8. And then centers, which is going to be a vector 3. And then extents, which is going to be extents 3D. Get rid of these two, right? And now we just have the two buffers, right? So all we really need to do here is just do offsets equals right binary. And we're not going to use the array version this time. So say block. The source is going to be the address of, or actually no, it's not going to be. Ooh, that would have been a nasty bug if I didn't catch that just now. Submeshes vertex data buffer, not the address of it because it's already an array. And actually, these are actually all wrong as well. These should not be the address of those things. It should just be that. Should just be the thing. And then offset is just offset, and then size is going to be total submesh vertex buffer size. And then we do the same thing once more with the index data buffer and total submesh index buffer size. Cool. And then this one gets replaced by a offsets plus equals right binary U32 block. And now we can just say K3D guard submeshes and then pass offset. And we don't need all this crap. Right? All right. And we only, we only write that if there are submeshes. that's a lot more, that's a lot less verbose, I should say. So we should probably do, yeah, we could actually do the same thing here. We could just do a right binary for the header. All right, so we can just do, this one is going to be the address of header. And then the size is just going to be size of K3D header. And again, you know, we can just kind of simplify our life a little bit. Start with the header first. Okay. So that's a lot better. Then we'll also do if header, what was the next thing that what was the next section? Submeshes bones. Okay. If we have bones, then we're essentially going to do this again. I'm actually just going to copy this because it's almost going to be the same thing verbatim. So this is going to be K3D guard bones. And then this is going to be bones name IDs and bones. Let's see, what was the other thing? Offsets. Offset matrices. Size of mat4. And then this just needs to be bone count in those two places. And I think that's actually it, I believe. Yep, just those two properties. So that's it for bones. And nodes are going to be the same thing. So node counts. This needs to be nodes. And then nodes. Oops. Nodes. Local transforms. This needs to be node counts. This needs to be node count. And I think I need also for the parent IDs, or parent indices rather. And that is also U16, I believe. Yep, it is. Okay. And there we go. So that is the node section. So next is going to be animations. And so again, that's going to be pretty straightforward. We just have a few arrays to write out and total channel count first, right? So if header dot animation counts, then the first thing we're going to do is, in fact, I'm actually just going to copy this again because it's going to get us most of the way there. So this is going to be animations. And then we're going to want animations. So name IDs is already there. The others we're going to have to change. And then this needs to be animation counts, animation counts, animation counts. Now, we do have this total channel count, which is just a U16. So actually, we should also have the ability to write that here. So let's just make a U16 version of this. Right. Just for convenience. All right. So now we can actually I'll just take a copy of that, paste it here, change this to the U16 version. And instead of that, we're going to have animations, total channel counts, which I think was what is in the spec. Yep, total channel count. There it is. All right. And so after that, we have, let's see, we do name IDs, durations, right? So that's F32s. And then ticks per second, right? And that's also, is that an F32? Yes. And then channel counts, which is going to be another U16. So do here, channel counts, U16. All right. And that's it for animations, right? Pretty straightforward stuff. Now, just like we said when we're deserializing, we do have the rule of if we have, you can't have animation channels without animations, right? So you have to have the animations, and then you can have the check within that to say header. Actually, it's not even going to be that. It's going to be animations total channel count, right? So we need to have obviously animation channels within there. So the animation channels themselves, this was the last thing that had, obviously we have a guard here to put in place. So let's put that in here first. So that's just going to be anim channels. There we go. And then we have all of these arrays, right? So we have two U16s, 6 U32s, and then we have the channel data buffer, right? So I'm going to grab these as an example. And what we're going to do is this is going to be channels for both of those. And instead of header, it's going to be animations dot total channel counts. Animations total channel counts. And then in terms of what we have here, we have name IDs, and then I think it was, what was the other one? Oh, animation IDs comes first, actually. So let's move this one down, and this is animation IDs. And this is also a U16. Yes, okay. And then we have some U32 arrays, right? So I'm going to separate these out just to make it a little bit easier to figure out what's going on here. So we do position counts and then position offsets, right? So position counts, this is a U32. And then position offsets, right? Okay, so we have this same thing. We have that same thing for rotation and scale, right? So we could just do rotation offsets, and then scale offsets, scale. Why did it do that? Counts. Okay, so position counts, position offsets, rotation counts, rotation offsets, scale counts, scale offsets. That all looks good. Okay, oops. So those are in the right order. The only other thing that we have to do is a binary write for the data buffer. So I'm just going to copy that from up here. And we're going to do that here. And we're going to say write binary. This is going to be channels. And it's going to be data buffer. Right, which is that. And then let's see. Did we did figure out, I think, what the channel buffer size, that's what it was. So this just needs to be channel buffer size. There we go. Okay. That should be it. Everything up until the strings table, at least. So, I don't know if we set... I think we're always going to have strings in this. So I think we're always going to write out we're always going to write out the string guard, I think. So write the strings up, the string guard. And then we'll do a offsets. Ooh. I just noticed a nasty bug in here. This should be always offset equals, not plus equals. That would have bitten me pretty hard. Gotta watch those copy pastas. All right. So we're going to do a write binary of this. The block, and then the source we are going to do serialized. Don't we have, oh, string table serialized. There we go. The offsets we're going to pass in, and then the string table size is going to be the last thing. So strings always write the guard, and then write out the serialized string table. Okay. And then that is pretty much it. The only other thing that we have to do is we actually need to go through and clean up all of the memory, all of the temporary stuff that we set up to write out to this, and then we're done. How do you highlight all the quality to fix it? Oh, equals. Oh, okay. So in Vim, I just did a search. Let me see. Yeah, they're still highlighted actually. So anytime you want to search for something in Vim, you just type / and then what you're going to search for. So if I want to search for double equals, I could search for that. Or in my case, I wanted plus equals. So I search for that, and then you hit enter. And then every time you hit N on your keyboard, it just bounces you to the next one. That's all it was. Okay. So, all of that being said, clean up temp structures, arrays, etc. before returning. All right, so this is pretty much done. The only thing I have left here to do is to clean up all of our temp structures and stuff so we don't leak that memory. So I can do that offline. And yeah, I don't even think we have any errors left to resolve in this file, which is awesome. So that is pretty much our format done. So now in the next stream, we can go ahead and start tying that into, loading animated and static mesh resources. We're going to be removing quite a bit of duplicated code between those two systems because we're going to combine those two systems into one to use this or to work with this. So I'll probably do the static mesh conversion first, actually, because we know that works. Just to kind of run all of this through its paces, and then we'll continue with the animated stuff after that. That's going to pretty much do it for tonight. Let me just catch up on some chat really quickly. Diamond, good to see you. How have you been? New here, how do you know you're not messing anything up? Is there another window you are seeing results or running tests? Nope, not yet. It's all up here. I do a lot of what I call dingus-oriented programming on here, where I screw stuff up in live on stream. I type things wrong or fat finger things, and I'm sure there's something I've messed up, and we'll figure it out. We'll write tests for some of this stuff where it really makes sense, but most of our tests are going to be the actual code, like the application code, and just running it, right? So, we do have tests where we need them for some of our core things, but for something like this, I think it's basically going to be we'll get it working on the happy path, and then we'll put some robust error handling in there where it makes sense to. But yeah, I hope that makes sense. Let's see. Okay. So I think I've caught up on. Oh, wait a minute. Is there a target game type the engine is made for? What type of game is the end game you want to make on it eventually? Okay, so the quick answer to that is we are going to be making a 3D isometric action RPG. And we've actually started like putting together a document for a bunch of this stuff. So there's actually been some design work done that we've started putting in place. And there is even a world map, which I actually don't have pulled up right now, but yeah, we actually do have plans to take something all the way to release with this. So coffee brewing simulators. I might put that in there for the memes. Retro you, how's it going? All right. All right, so let me find somebody to raid. And while I do that, I just want to say a big thank you to you guys being here, following along, interacting, and all that stuff. I actually know who I'm going to raid, and I better raid them before they raid me. We're going to raid Els Dragoon. They are a duo who is writing a game for the NES in 6502 assembly. So we're going to go and raid them. Yeah, thank you guys so much for being here. If you haven't followed me already on the Twitch or YouTube side, I would greatly appreciate that. Or both if you're so inclined. But yeah, otherwise I'll see you guys later.